Okay, so welcome everyone to our third master seminar. So today's speaker will be our own Chris Nemeth, and he will talk about optimization on the space of probability measures.
Okay, great. Can all the people online hear me? Okay.
Yep.
Great.
Sounds
Okay.
good.
Excellent.
It's going to do. Oh, okay, sorry.
Okay. Are we okay now?
I think it should be fine. Yeah.
It'll be fine. Okay. Yeah, I guess that's okay. Sorry, I'm just going to move this thing that's in my way. Right. Okay. So yeah, is there a way I can sort of make it full screen here?
Yeah, okay, that's what I was.
Oh, you did that. Can you pop out? What does that do? Better? Maybe.
Actually, no, sorry, we should.
Does that work? Oh, just...
No, sorry. I think that was. Shit. There should be some easy full screen thing, right?
Probably for that.
I think.
Well, what happens if you click the three little dots?
Settings and more.
And then next to Zoom, the
This one, I think I just clicked,
reset.
but it doesn't.
We can all look at this, right?
Yeah.
I suspect when I switch the slides, how's it look? It looks fine. Yeah.
Yeah.
We could be here till Christmas at this point. So.
Sorry. Yeah, that's something I didn't expect.
That's okay, it'll be fine. Okay, great, that's good. Going. Yes, okay, thank you for coming. So this is joint work with my collaborator Louis, who's a lecturer at UCL. So what I'm going to do the talk, it's going to be a little bit half about trying to set up this idea of optimization in this space of probability measures, and then the second half I'm going to talk about some sort of recent work that we've done, which sort of looks at this idea of there's lots of really cool stuff in optimization, machine learning, and it's an area that's very heavily studied. But in the sampling space, if you think about like Markov chain Monte Carlo type algorithms, that area isn't as perhaps well established. And so when you kind of bring these two ideas together, this optimization, these sampling under one framework, you now have this kind of nice translation of being able to sort of move some of these cool machine learning optimization algorithms into this kind of like sampling context. That's kind of the old, that's the whole point of this talk, I guess, in sort of one sentence. So for those of you who are not sort of machine learners, this is like everything you need to know about machine learning in one slide, right? And once you know this, then everything else is trivial. So basically, the way machine learning sort of works is that we assume we have some data. So we have Z and Y. So Z would usually be some sort of input, so pictures of cats, and Y would be a response, so a label. Is it a dog or is it a cat? Okay. And what we do then is, once you have some data, we then choose a model. I'll call it G. Now, your model might be a linear regression model. It might be a random forest, but nowadays it's usually some kind of neural network. And the idea is that you plug your cats into your model, and out comes a label, which is yes, it's a cat, or no, it's a dog. Okay. Then what we do is we then need to train what machine learners call it training. Statisticians would call this inference. So you want to learn what are the parameters of your model. And as statisticians, you would look at things like maximum likelihood estimation or sort of learning a Bayesian posterior distribution. Machine learners look at this in terms of minimizing the loss function. So what you want to try and do is you want to say, well, I've observed these labels, let's say sort of cats and dogs. And what I want to do is if I plug in some random image, okay, do I accurately predict that? Okay, and what I want to do is I want to train the parameters X, my model, such that I minimize this loss. Okay, so if you want to train, say, ChatGPT, then what you're basically doing is you're taking lots and lots of data, you're trying to minimize some error, okay, and you're training the parameters of that neural network such that you minimize your error, okay, and the last bit, which is the most important bit really, is actually how do you do the training bit, right? So the first three bits are easy. You've got the data, pick any model off the shelf, choose a loss function. There are lots of others. I've just chosen a L2 loss here, but there are different ones you could choose. But the really hard part is actually how do you actually do the training bit, actually. So how do you actually learn some parameters, which I call X star, such that you minimize this loss function? Okay. And as I said, there's been a huge amount of work in the optimization literature, going back to the 1950s, where people try to use techniques to try to find what are the parameters which minimize this loss landscape. Okay, so this is this is my loss function that you see here, and what I want to do is I want to try and find the point in the loss function which minimizes the loss, which gives me those parameters which in theory should give me the best sort of predictive accuracy for forward tasks that I want to do. So we have Meher joining later in the year. So Meher is actually an expert in optimization, so he knows a lot more about this than I do. But what you're basically trying to do in optimization is you say, I've got some loss function, this f that I want to minimize, and I can minimize that by thinking about what's the ordinary differential equation for the gradient flow of this loss function. But unfortunately, this ODE, you can't generally evaluate it analytically, and so you have to do some kind of numerical approximation. And the simplest numerical approximation is just to do an Euler discretization. Okay, and this is the sort of standard sort of gradient descent algorithm, where in practice, machine learners will tend to do something called stochastic gradient descent, and they just try to approximate this gradient with some sort of approximation. And the reason you want to do stochastic gradients is because if you've got, 1 billion data points, you're not going to want to calculate this new gradient for 1 billion data points every time you update the gradient. Okay, so what you can sort of see is that I just initialize this mountain point, and as I run this algorithm, what you'll see is I take the gradient of the loss function at xt, and then I update it by moving in the direction which will minimize the loss. Okay, so moving in the direction of the negative gradient, and you run this for long enough, and you can show that it will converge to a local minima of that loss function. Okay, so it's really, really, really simple algorithm, and there are lots of results now to show rates of convergence under different types of loss functions, if it's a smooth function, if it's convex, and such and so forth. And so it's been very, very well studied now in the optimization literature. But more recently, people tend not to use something as simple as this. In practice, people would use more sophisticated algorithms like ADAGRAD, which are adaptive gradients, or ADAM, which is sort of a version of ADAGRAD, or RMS prop, or shampoo is the new sexy thing. The shampoo thing is a joke, but anyway, I can talk about that later if you're interested. Suffice it to say, there are lots of these algorithms, and what we're all trying to do is we're trying to start at some boundary point and to find the minima as quickly as possible. Okay. Why do you want to find the minima as quickly as possible? Well, as you can imagine, these models are getting huge, right? You're talking billions and billions of parameters. That's even for small models. A small model will have, say, 7 billion parameters. These are for large language models, I should say. So trying to learn what is the minima of this loss in this 70 billion parameter space is, as you might imagine, quite computationally expensive. And so there's been a lot of interesting work looking at how much it actually costs to just run these simple optimization algorithms. And actually, you can save literally millions and millions of dollars by actually just doing this thing correctly. Okay, because you can imagine that if you choose a bad optimization algorithm, or I'll just take a sort of step back, if you choose this sort of step size parameter, sometimes called learning rate, if you choose this inappropriately, it's going to cost you millions of dollars running your training on your GPU. Okay, just to illustrate what I mean there. So if I go forward. It goes so slow. So how you choose this sort of step size parameter, which they call the learning rate in machine learning, is really important. So what I have here is a little animation which sort of shows that on a very simple one-dimensional convex function, you can sort of see that if you choose this step size parameter to be too small, what happens is you make lots of little steps, and it takes a long time to converge to the minima. And this is you wasting your GPU hours and Microsoft spending lots of money. If you choose your step size to be sort of too large, you have a higher discretization error on the ODE, then what happens is this thing will just diverge completely. And so the kind of Goldilocks principle where you want the step size to be chosen such that you find the minimum as quickly as possible. So you can sort of see in the animation here, this middle one where I've chosen the step size to be 0.4, you can sort of see that I converge quite quickly towards where the minimum is, and it only took me sort of 3 gradient steps rather than whatever it is, 50 or something for that one. So how you tune these things makes a big difference in terms of both theoretically in terms of their convergence and also just practically in terms of how long it takes to run these things and how much it actually costs when you're training these big large language models. Okay, so that everything I've just told you there is about trying to learn a point estimate. So you're trying to learn one set of parameter values which minimize your loss function. So if you're a statistician, you would think of this as being the equivalent of sort of maximum likelihood estimation, right? So minimizing this loss function is equivalent to maximizing likelihood function. So that's what you do if you're a frequentist. But there are many situations where we actually want to learn a whole distribution. So one such situation is in Bayesian inference. So in Bayesian inference, we care about a posterior distribution, which we often define in this sort of notation here. So pi, throughout the rest of this talk, is going to be some sort of density where I want to estimate. And I'm going to define it in terms of exponential of some negative potential function. Z is a normalizing constant, which doesn't depend on x. Now, for Bayesians, what this actually means is that your u, this normalizing constant, is basically a log likelihood plus a log prior. Okay? So there are lots and lots of different techniques out there in the sort of computational statistics literature, which will show you how you can approximate this distribution. So this is what's given in the sort of black line that you see here. And if you use algorithms like Markov chain Monte Carlo, these sorts of sampling algorithms, you can sort of show that under certain conditions that these things will converge and they will give you samples from pi. Alternatively, you can use deterministic approaches. So you can use these things like variational approximations or Laplace approximations, or even if you look at the map estimate, that's the maximum a posteriori estimate, that's just the point which maximizes the posterior, which is a little bit like the simple setting we had earlier where we're just trying to find one point that minimizes the loss function. Okay, so the equivalent of just finding a point that minimizes the loss function would be finding a point which maximizes your posterior distribution. Okay. So there are two paradigms in statistics. There's the frequentist approach, which is you treat your parameters as being fixed. You want to learn those fixed parameters. And there's the Bayesian approach, where you assume that your parameters have a distribution, they're not fixed. So when you assume that your parameters have some sort of distribution associated with them, it therefore means that learning that distribution is just much more complicated. Another situation where you want to learn a distribution is in what we call mean field neural networks. So with neural networks, it's an interesting feature, actually, where if you think about, you have inputs and outputs, then in the middle, you've got a whole bunch of like connections and bits of, translations that you're sort of doing to your data. So you put your data in, you do some nonlinear transformation of that data, and out comes an output. Okay, so your input could be bits of cats, and your output will be, is it a cat or is it a dog? Okay. So what you can do is you can construct your neural network in terms of these neurons. So the neurons are these sort of circles that I've got here. And the output you get is then just going to be a combination of the neurons that go from sort of left to right. Okay. But what's interesting is that if you let the number of neurons, so if you take this hidden layer here, the blue ones, I've got 4 here. If you let the number of neurons go from 4 to infinity, then what happens is rather than having this sort of summation over the neurons that I have here, I now have this integration. Okay, and I now have a probability measure mu, which now represents the uncertainty that I have in these weights. So rather than trying to learn weights, I've now got a distribution of these weights instead, right? Now you might think, why the hell are you doing that? Have you not just made your problem a lot harder because you had 4 weights and now you've got a distribution you need to learn instead? The reason you might want to do this is there's a really cool result from 2018, which basically shows that in this what we call mean field limit, where the number of neurons goes to infinity, you can basically show that when you minimize your loss function, that loss function has a global minimizer, right? In the measured setting, not in the traditional setting where you have your 7 billion weights that you're trying to estimate. That is a very non-convex landscape. But in this setting, you actually have a global minimizer. Okay, so there are some advantages to actually looking at things in this infinite dimensional limit rather than just trying to do optimization on the finite dimensional space. Okay, so again, same problem here is how do we learn some distribution of these weights which are optimal in some way? Okay. Right, so the question is how do we learn distributions? So I'm just actually going to, this might be dangerous, I'm going to switch to a little animation. Okay, so the way people tend to learn distributions in statistics is use these Monte Carlo type algorithms. So what I have here is a two-dimensional distribution. Okay, so I have an x and y, and the contours give you what we sometimes call the banana distribution. It's actually a warped Gaussian. And what we do is we create a Markov chain using different types of proposal distributions. But what happens is we basically pick a point, we perturb or propose another potential point, and then we accept or reject depending on whether or not that proposed point falls inside the distribution or not. Okay, so this banana thing you see here is the distribution I want to be able to sample from. Okay, so this is my pi. Okay, and I've got a whole bunch of different algorithms at my disposal. So one is this simple one, which is called the random walk, and the random walk is it's like the drunkard's walk. It's basically randomly. So you start at a particular point. So you are currently. The mouse is so slow. If you're currently here, then what's happening is you're within this sort of Gaussians, that's what these circles are. So within that Gaussian, you randomly propose a point. If that point falls within the contour, it means contour within this posterior distribution, then you'll accept it, and then you just move on from there. And so if I just sort of put this thing on steroids, what you should see is that, I can go faster than that, can't we? Yeah. Then what happens is if you just sort of run this thing long enough, what you'll see is these points form a Markov chain, and that Markov chain then begins to approximate the distribution. Okay? Alternatively, we might say, well, there are better algorithms than this random walk thing because that's just like blindly sort of bouncing around. We can do more efficient things, like we could use gradient information. So what we're seeing here, sort of slow it down, is that what's happening is you're taking a current point in your distribution, you're calculating the gradient, you're then moving in the direction of the gradient, plus a bit of noise is being added on as well. And again, if you run this algorithm, then it will give you sort of lots of samples from your banana distribution. This is generally how we've been doing sort of Bayesian statistics for 30, 40 years now. We've been coming up with clever ways of creating these Markov kernels, such that we can explore these distributions as fast as possible. Okay, and this tab I've got here gives you a whole bunch of different algorithms. There are lots of other ones to sort of choose from, but these are all sampling-based algorithms. Okay, so when I say sampling, what you're doing is you have a point and you're sort of randomly perturbing around that point in some clever fashion. Okay. I'll just show one more because this last one's going to come up later on. The other one is a sort of interacting particle situation. It's called the Stein variational method. And what you do here is you basically select a bunch of particles randomly. Each particle you calculate the gradient. And what you'll see is that the particles now moving in the direction of the gradient until they find the distribution. And then there's a sort of kernel which repels the particles to kind of force them apart, which is why you see they kind of move into the tail. So they're kind of like an attraction repulsion scheme where they're attracted towards areas of higher posterior density, and then when they get there, they kind of repel each other. Okay, so this sort of interacting particle approach with 100 particles evolving in some way, it's quite different to. I'll go back again. It's quite different to something like actually, that's too complicated. I don't want to talk about that. It's quite different to a situation like this, where you just have one Markov chain that you're just running for an infinite amount of time. Okay? But these all come under the same umbrella as being sort of sampling algorithms, and the way that we analyze these sampling algorithms, there's a whole toolkit that we have for doing this. I'm not going to go into it today, but what I'm going to sort of suggest is actually all these sampling algorithms and maybe aren't actually sampling algorithms, and maybe they're actually optimization algorithms. And if they're optimization algorithms, there's a whole bunch of sort of theoretical tools that we can take from the optimization literature and now apply to understand the properties of these sampling algorithms. Okay, so move back to my slides. Okay, so as I just sort of mentioned, there's a whole bunch of these different sampling algorithms. So the random walk, you just pick a point in your distribution and you just perturb it with Gaussian noise. The Langevin scheme is you have a particular point, you move it in the direction of the gradient. So this u is the potential function. Okay? So if you take the gradient of the log posterior density, that gives you the potential, or the grade of the potential function. So what this algorithm is saying is that you start at your current point, you move in the direction of the gradient, plus you then add on some noise. There's another scheme which is very popular for the last 20 years or so, it's the Hamiltonian Monte Carlo scheme, which uses Hamiltonian dynamics to explore distributions. And then the last one is this Stein variational method, which is this sort of like interacting particle thing that I sort of showed you. But what's interesting about all these algorithms is that they all have these little tuning parameters, which you can call learning rates or sort of step size parameters. And how you actually choose these step size parameters has a big impact on, do you converge within 100 or 200 iterations, or do you just not converge at all? Okay, so what I'm going to do in this talk is I'm going to talk about a paper which we just finished last week. And in that paper, we basically show that even though these algorithms are very, very different, you can actually, by viewing them as both of them being optimization algorithms in this space of probability measures, you can actually find some optimal ways of tuning the parameters for this one and this one using the exact same techniques, even though they're quite different algorithms. So what do we mean when we say optimization in the space of measures? Okay, so normally those sort of sampling schemes like MCMC, you're trying to generate a Markov chain, which the samples will give you in, if you run the Markov chain, then the samples it gives you will approximate the posterior distribution in some fashion. Instead, what we might want to try and do is actually, can we just view this sampling problem as an optimization problem? So earlier I said that in optimization, you're trying to minimize loss function. Okay, so your loss function is you put in some different parameters and it gives you a different loss, and loss, if you put in the right parameters, the optimal parameters, then your loss will be sort of minimized in some way. Instead, can we reframe our sampling in the same way? And one way to do that is, rather than having these loss functions that we're trying to minimize, we have a loss functional. Okay, and the difference between a function and a functional is that for a functional, we're putting in a measure distribution instead of vectors. Okay, so in this particular case, you can just, in fact, for the rest of the talk, in fact, you can just imagine this functional as being the Kullback-Leibler divergence. Okay, there are lots of different functionals that you could choose. Now, earlier when I had the simple loss function for optimization, I just had this L2 error. So I was looking at what's the error between what I have and what I predict. Now, because I've got distributions, I need to find a way of measuring the difference between distributions. The Kullback-Leibler divergence is one measure of similarity or dissimilarity between distributions. So KL, and this is the KL divergence from mu, which is just some measure, and pi, which is the thing I care about. Okay. So what I'm going to try and do is I'm going to try to minimize this functional. So I want to try and find the measure mu, which minimizes the distance from something I have to something I care about. So I care about pi. And just to kind of give you an illustration of what this kind of looks like, if you imagine what I have at the bottom here, this blue space, this is my space of probability measures. So these are all probability measures which are finite at the moment, what T stands for. And this red sort of concave function you can see here is the Kullback-Leibler divergence. And what you can sort of see is that there's a trajectory I can take from some initial random measure, probably naught, and I can take it along a path, this is geodesic, which will take me from some random initialization to pi. Pi is the thing I care about. Okay, and you can sort of see when you look at this bowl that the Kullback-Leibler divergence decreases as I move this measure from out here towards pi. Okay, so what I'm basically trying to do is I'm basically trying to say that all those sampling algorithms I had before, maybe they're really just doing this. Like maybe they're just minimizing the KL divergence. And if that's all they're doing, then can I use optimization algorithms or ideas from optimization to try to prove some interesting stuff? Okay. So just to sort of compare the two schemes together. So this is your traditional machine learning, I want to train ChatGPT approach. So I want to minimize some loss function F, I can derive the gradient flow, and then I just do discretization, which gives me stochastic gradient set. Okay, and I run this algorithm. If I run it long enough, then eventually this thing will converge, and I'll have some x's which minimizes loss function. Okay? So that's how we do it in the Euclidean setting. But now in the sort of batch design space, we now have the minimum of some functional. So just keep in your mind Kullback-Leibler divergence. Now, I want to do the same trick. Okay, I want to figure out what is the gradient flow for this functional. Now it gets a bit tricky because the gradient affects some geometry. Now in this case, I'm choosing the Wasserstein space to be my geometry in this case. And if I could do that, then are there some sort of conceptual, are there some sort of gradient descent type algorithms that work on the measure space? And I'm sort of doing some like, what's called bunny ears. speak from, because this thing doesn't actually make sense. Right? I mean, you can't just say, oh, I'm going to take the gradient of this functional and I'm going to start pushing these measures in the direction I want them to go in. So this is conceptually what we want to try to do, but how do we actually do this in practice? Well, the first challenge is like what actually is a gradient when you're talking about these functionals. Okay, so if I have this Colbert-Leibler divergence, what does it mean to take a gradient? Well, the way that we do this is by just considering what's the first variation of the function. Okay. So there's a result from Ambrosio in 2008. There's a book called Gradient Flow Methods, I think it's in chapter 10, which gives this result. I'm not going to go into the result in details now, but suffice it to say, there's a way of showing that if you take the gradient of the functional with respect to the Wasserstein metric, then that is equal to the first variation of the function. Okay, so what's the first variation of the functional? Well, basically what we do is we take our functional, okay, and we just perturb it. Okay, so we have some measure mu, we can perturb it, and then we can just look at, well, what is the sort of limit as this epsilon I've introduced, as this epsilon goes towards 0, and that perturbation of that functional gives us our gradient. So we sort of think about the way we think about gradients in Euclidean space. You sort of say, well, I've got a point here, I've got a point here, and what happens as the distance goes towards 0, and you get a gradient. It's the same idea, except we're now doing this in this functional space, which is a bit more complicated than the sort of traditional Euclidean space. And so you need to use a bit more tools, I guess, to try to derive what actually gradients mean. Now, for what I'm going to talk about, I'm mostly going to focus on this situation where we're taking this gradient with respect to Wasserstein geometry, but actually you don't have to. Actually, there's a whole bunch of other algorithms out there which replace this geometry with something else. So we have like Stein geometry or Fisher geometry or the Wasserstein-Fisher-Rao geometry. There are a whole bunch of different ones you can choose. And depending on how you take this gradient, it gives you a whole bunch of different algorithms. Okay. But the main point to sort of make here is that there are ways of sort of calculating the gradient of this functional. Okay. So if we can calculate gradients, then what do we do with that information next? Well, what we're essentially trying to do is we're trying to solve an optimal transport problem. So we're trying to move our distribution or sort of mass from one place to another. So you can sort of think of this as being how you initialize, this is your pi that you care about. Well, how do I move my measure from some initial distribution to the thing I care about? Okay, so I need to create some sort of path. One way to do that is to think about the continuity equation. Okay, so I have some sort of collection of measures mu t, okay, and each of the measures will have a velocity field associated with it. And excuse me, and what I want to try to do is I want to try and take my measures and I want to move them from some initial distribution to the pi I care about. Okay? And the way we want to do that is in a way which sort of satisfies the continuity equation, because we could take some initial measure and we could send it somewhere, okay, but sending it somewhere doesn't mean it's actually going to converge to the thing we care about on the right-hand side, okay? So we need to enforce some constraints, and the way to enforce those constraints is to use the continuity equation. So what the continuity equation tells us is how does that measure change through time, given that we've chosen some velocity field v, okay? And we have a choice of how we choose that velocity field, okay? And one way to choose that velocity field is to say, well, we want to choose our velocity field in such a way that is going to decrease our function. Okay, so remember our function is this sort of KL divergence. So we want to try to minimize this through time, okay, as we sort of run our algorithm. And what you can sort of show by, it's quite simple, by the chain rule, is that the time derivative of the functional is given by what we have here on the right-hand side, which is the Wasserstein gradient of the functional with the inner product with the vector field. And if we choose that vector field to be the negative gradient, so you remember thinking back to what I was saying about the gradient flow, and I said with optimization, you have this loss landscape and you want to move in the direction of the negative gradient, right? So you want to find a way of minimizing your functional. So choosing your velocity field such that you're minimizing or moving in moving in the direction of the negative gradient makes sense. And so if you take this velocity field and you plug it back into here, what you have is something like this, right? And the fact that this time derivative is less than 0 tells us that we are monotonically decreasing our objective function. Our objective function is our function. Okay. So what all of this is trying to say is that I have the continuity equation, which tells me how mass evolves from time 0 to time t, let's say. And I want to constrain how I evolve my measure such that I don't have mass escaping, I don't have new mass coming into the system. So that's why I use the continuity equation to ensure that I have that I ensure those constraints of not losing mass. And I've iterated how I choose the velocity field in terms of how I actually move my mass, and I choose to do so in a way which minimizes the function. Okay. Right, that's basically all that means. So therefore, when you put all those bits together, what this tells you is that the Wasserstein gradient flow is going to be determined by our velocity field, which is the negative gradient of the functional. And when you plug that into the continuity equation, what you now have is this. Okay? So what this tells us is that my change in my measure is going to be determined by the gradient of the function. Okay? Now, the question is, if you have this set up, okay, so you have this connection between how the measure changes and the Wasserstein gradient flow, how do you do anything useful with this? Like, how do you actually create a practical algorithm which is useful? Okay? So, so this is where the sort of connection between sampling and optimization sort of comes in. Everything I sort of set out is quite abstract. And so in terms of actually how do you make something practical with this, what we can now do is we can go back to the sort of sampling algorithms we had before. So I mentioned you have this sort of Langevin scheme and you have this Stein scheme. So this is the one where you've got the particles kind of evolving through your distribution, and you've got this other one where you have this collection of particles which are interacting in some way such that moving the particles in a direction which increases the sort of posterior density, but this repelling term which forces the particles to move away from each other so they don't all clump together. Okay. Now the question is, even though these are, they're quite different in terms of how they operate as sampling algorithms, are they actually just doing this? Are they actually just trying to solve this optimization problem where if I can find the measure which minimizes this functional, is that actually just giving me my distribution pi that I actually care about? Okay. So just to give you 2 examples of this. So for the Langevin algorithm, so this is what I set out earlier. I said this is what my Wasserstein gradient flow looks like. I want to minimize some functional. I've got this idea of a gradient flow, okay, in terms of how my measure evolves based on the negative gradient of the functional. And I have this kind of like conceptual gradient. So I want to sort of move my measure in a way that minimizes this function. Okay, as I said, this is kind of like a conceptual thing, it's not a real thing. So how do I turn that into a real thing? What you see on the right-hand side is I'm actually running this Langevin algorithm on that loss function I had at the very beginning. And what's nice about this is if you remember back to the optimization setting, I think the optimization started here and it kind of went downhill and it kind of found this minimum and then it sort of stopped. What's quite nice about the sampling type algorithms is that you're able to explore between different modes. Okay, so you have much better exploratory capacity in order to actually explore more regions of loss function, let's say. Okay, so if this is my setup, then how does it work in the Langevin setting? Well, in the Langevin setting, the first thing I have is I choose my functional to be the KL divergence. Right? Now, you don't have to choose KL, you could choose other things. You could choose Renyi divergence, chi-squared divergence, maximum mean discrepancy. There's a whole bunch of different ones that you could choose. But for the Langevin setting, we're going to have the KL divergence. So then what is this gradient flow? So if I take the gradient of this thing with respect to the Wasserstein geometry, then what I have is that the gradient is going to be the gradient of log posterior, subtract the gradient of the measure at some particular point, time t. And if I take this gradient, remember that my Wasserstein gradient flow is based on my continuity equation, plugging in a particular choice of the velocity field. Then if I take this gradient, I plug it into my continuity equation, does anybody want to have a guess what I get? I'm just asking the questions so I can do this. Want to guess? Okay, Fokker-Planck equation. So when you have the KL divergence of your functional and you take the gradient in this way, plugging this into your continuity equation just gives you the Fokker-Planck equation. Okay, and I'm not going to go to the proof now, so I just don't have enough time, but it's possible to show that with the Fokker-Planck equation, that tells you how your measure changes. If, however, I pick out a particular point, x, from my measure at time t, then there's a stochastic differential equation, which is the equivalent of the Fokker-Planck equation, which tells me how that particle evolves. Okay, and that stochastic differential equation, once you discretize it, is this form. Okay, so if you let this discretization term, if you let this gamma go towards zero, this converges to a stochastic differential equation. It's called the Lancaster diffusion, and the Lancaster diffusion has the same we'll give you the same marginal distribution as what's given by the Fokker-Planck equation. Okay, so you can use there's an equivalence of going from the change in the measures to the change in the particles that are simulated from that measure. Okay, so that's nice, because what this basically means is I had this to begin with, I had this sort of sampling algorithm, this launchment thing, and what I can basically show is that when I run this algorithm, this thing, I'm basically just solving this. I'm basically just solving this minimization problem. Okay, so that's for the Lancaster setting. The other setting is the Stein variational setting. So in the Stein variational setting, I again have the KL divergence of my functional, but now when I take the gradient, I don't do it with respect to the Wasserstein geometry. I do it with respect to this Stein kernel instead. So this is the Stein geometry. Turns out you get a slightly different gradient, and when you take this slightly different gradient, you plug it into the continuity equation. You do the same hoops and jumps, you end up with this Stein variational gradient descent method. Okay, so you end up with this particle-based approach, and you sort of see that as I evolve these particles, they sort of expand and they try to explore this loss function. Okay, and again, what's really nice is, I'm again solving the same problem, still trying to minimize the trivial divergence, but now I just happen to have a different algorithm, and I get a different algorithm simply because I've chosen a different geometry. But they all fall under the same framework. And in fact, in the machine learning community, there's been a lot of activity in the past 10 years or so looking at different variations of this. And what these all basically boil down to is if I have a different functional, if I have a different way of taking the gradient of that functional, then I get a whole bunch of different algorithms. Okay? But they all fit under this same umbrella. Okay, so the interesting question which we're sort of interested in is how do you actually choose what this sort of step size parameter should be? Okay, so I mentioned that when you have this Lancaster scheme or you have this Stein scheme, they both contain this kind of step size parameter, and how you choose this parameter is a bit of a mystery. So what people try to do is you just pick a gamma value, run it for a while, did it work? Maybe pick another value, run it again, did it work? It's very much trial and error. What we would like to do is try and figure out what is the optimal choice for this step size parameter. So the question is, well, how do we define optimality? So we came up with an algorithm, which I actually called Fuse, and this is really to keep Henry happy. So Henry always says we need an acronym. And the way we do it in this paper is to look at what is the upper bound on this functional, so the KL, what's the upper bound? And once you find the upper bound is given in terms of the step size parameter, so can you just minimize that upper bound, okay? And if you minimize that upper bound, that gives you kind of the optimal step size. And I'll show you how we do that in a minute. The paper we put on archive last week is quite short. It's only 95 pages, so it's definitely worth reading. But we actually, so the way we wrote it is that if you just read the introduction, you don't need to read the rest of the paper. But you should read the paper anyway, because it's wonderful. But the details in the paper if you're interested. Okay, so we have to make a few assumptions before I explain how the sort of theory works. So the most important assumption we have is we have to assume geodesic convexity. So when you think about functions, if you think about optimization, it's quite common that when you try to prove optimization results, you often assume that the function you're optimizing is convex. Okay. Now, here things are a bit different. I don't have a function, I have a functional. Okay. And so we have to have a slightly different definition of convexity. But if you look at this, don't worry too much about the details. But if you sort of think about what is convexity for functions, it's quite sort of similar definition. But now it's for the measure space rather than the sort of Euclidean space. The other assumption we require is that all the gradients are bounded in some way. Okay? And the last one is, this is like an optional. We prove it in two ways, with and without this assumption. But one assumption is you can have that the potential function is smooth. Okay, so you don't have strange discontinuities in your potential function. What we have in the paper there's a way of proving it start again. So you need one of these two. Okay, you either need boundary gradients or you need to assume smoothness. Okay, you can have both. That gives you a slightly different result. But if you drop the smoothness, what's interesting is that you actually get the same result as if it's smooth. And I'll explain why sort of later on. But these are quite common assumptions that you see in the optimization literature. So I think what's interesting is that when people try to prove things for these sampling algorithms like random walk or Launchman schemes, they tend to do everything in this infinite dimensional setting. They say, well, what if my posterior distribution is of infinite dimension, then what happens? But the way they do it is kind of odd because they have to assume that all the dimensions are independent of each other. And so they have these kind of weird assumptions, whereas these assumptions are a bit more natural, and it's a bit easier to sort of assess, are these assumptions true in practice?
But just a quick question about the 2A assumption. Is it like, so this inequality holds an expectation or holds a probability one?
So these are, yeah, so these are like stochastic gradients. So you think about this as like stochastic gradient descent. All you're just assuming is that if you take your gradient and you perturb it by some noise, then it's still going to be bounded, right? So this happens when we have a huge amount of data. You don't use the full data when you calculate the gradient. So you take a subsample of the data. You just want to make sure that that is going to be finite, that gradient. You'll see why it has to be finite in a minute. Basically, it turns out that we use the gradient in the denominator, and if it's not finite, then everything doesn't work. But yeah, it is in terms of expectation though. So I'm not going to go through how we derive the result. I'll just give you what the actual result is. So so we proved this for a few different algorithms, but using this sort of same general framework. The result that you have for the unadjusted Launchman algorithm, so in the Launchman setting, what you have is your functional is the KL divergence, and your posterior or your distribution you care about pi is the exponential of this potential function u. If you run your algorithm for capital T iterations, you can put an upper bound on the KL divergence. Okay, so after I run this thing for T iterations, I've got some approximation for the distribution. How far is that approximation from the truth? Okay, and this upper bound essentially has two key terms. One is the Wasserstein distance from where you initialize to where you end up, because you can imagine that, you know, if my posterior distribution is here, then actually me starting my algorithm from here, I'm going to get much faster convergence compared to if I start out here. Okay, so how far away do you initialize from where the true distribution is? And then the second term is essentially determined by the gradients that you take as you're sort of evolving the algorithm. Okay, and what you notice is that both of these terms contain this gamma parameter. So this gamma parameter is a sort of step size parameter. So what we could say is, well, I want my KL divergence to be less than some sort of epsilon. Okay, so how do I choose my gamma such that I minimize this upper bound? And it's quite trivial to do it. All you do is just, take the derivative of this thing with respect to gamma, set it to 0 and solve it. And once you do that, you find that the optimal step size parameter should be given by the Wasserstein distance from where you initialize to where you want to end up, and the sort of square root of the sum of the gradients. Okay. Now, that is completely useless, right? It's completely useless because if I knew this, then, if I knew this, I could calculate this. I don't know this, I can't calculate this. And for this thing, these are all the gradients I have. I need to know all those gradients from where I start to where I finish. And again, I don't know what they're going to be in terms of on the algorithm. Okay, so this thing is completely useless. But if it wasn't useless, if you actually took this optimal step size parameter, if you plug it back into this upper bound, what you then have is an upper bound on the KL divergence, which is given by this term here. And the reason I'm showing you this is because assuming the gradients are bounded and assuming to set the Wasserstein distance to be d, just for simplicity, then what you can sort of show is that the KL divergence is going to be determined by this sort of distance term and this square root of t. Okay, the reason you get, I won't say where the square root of t comes from. You just have to trust me, you get the square root of t. This is important because this basically gives us the rate of convergence. This tells us the rate at which we're converging our approximation for pi, which is mu. The rate at which mu is going to pi is going to be square root of t. Okay, so t is the number of iterations I have for my algorithm. But what's really interesting about this result is that whether you have a smooth or non-smooth functions, you still get the same rate or same order of convergence, which is 1 over root t. And the reason this is quite interesting is because when you look at the exact same analysis in the optimization setting, when you're non-smooth, you have this result, but when you're smooth, so your function is smooth, then you actually have 1 over t. But when you look at this in the measure space, you always have 1 over root t, regardless of if you're smooth or if you're not smooth. And the reason is because when you run this Launchman algorithm, it always has a non-asymptotic bias that you can't get rid of. And so that non-asymptotic bias basically means that you have a solid convergence rate. Okay, so that's kind of interesting. So it's something which came out of the analysis, which we didn't know about before. Right, so in the sort of 5 minutes I've got left, I mentioned to you that you can derive what the optimal step size parameter is, but it's completely useless. And the reason it's completely useless is because if I take this black line to be my functional, then what I want to do is I want to start my measure at some point, okay? And I want to find pi, and pi is the point which minimizes my function, okay? Now, I don't know what this is. If I knew what this was, then why am I bothering? I do know what this is, but I don't know what the distance is. Okay, so I don't know how to do anything with the numerator, and I'm also in trouble with the denominator because the denominator requires me to know all of these gradients from time 1 to time 2. Okay, so I need to know what all these gradients are going to be along the way. Okay, don't know that either, right? So this thing is partly useless. So what we did was we have this algorithm, which I said called Fuse, and what we do with Fuse is we basically try to learn that numerator and denominator as we're running the algorithm. Right? So when you initialize, what happens is you make a step and then you update, well, what is the maximum distance I've traveled so far? So I've gone from here to here, that's the maximum I've seen so far. And if I take another step, then that maximum just increases. Okay, so remember that I actually want to know this to this. I want to know what's that distance. So what I'm going to do is as I run the algorithm, I'm just going to keep tracking what is the maximum distance I've traveled. Now, if I'm here, because I've got noise, if I were to go backwards, I would still keep this. That's still the maximum of what I've seen so far. Okay, so that's fine. So I can just run it, and I just keep tracking what's the maximum I've traveled so far. And then for this sum of these gradients, I just make a truncation. So rather than having all of them from 1 to capital T, I just store all the ones I've seen so far. Okay. And if I do that, then I now have this more practical step size scheme, which is basically what's the maximum distance I've seen from where I start to where I want to go to, and what is the sort of the sum of the gradients that I've seen so far. Okay, not all of them, but just what I've seen so far. Okay, and it turns out that when you use this algorithm, what you find is that this optimal, the upper bound rather, you get sort of KR divergence is sort of similar to what you had before. So I said that you have this 1 over root t result. But now we've got this additional logarithmic term. So this logarithmic term is basically the price that we're paying for not knowing the optimal step size and using this kind of approximate step size instead. We have to pay some sort of penalties. Okay. So this is quite a nice result. We get, as I say, same convergence that you have in the optimal setting, but now there's just this logarithmic penalty we have to pay. So just in the few minutes I've got left, let's give you some examples of how this thing works. So if we take a simple logistic regression example, what you can sort of see is that this is SGLD, so this is a stochastic version of the Launchman algorithm. And what you tend to do is, because you don't know how to tune these step size parameters, what you would do is you just select a grid. So what you see on the x-axis are a grid of different step size parameters, and on the y-axis I have predictive accuracy. So how good is my model? Okay, so I want my model to be super good. So I want 76% accuracy, let's say. And what you sort of see for this algorithm, this Launchman scheme, is that if I choose the step size in just the right way, so if I choose it to be somewhere in this region of 10 to the minus 6 or 10 to the minus 7, then it works quite well. Whereas if I set the step size to be too big or too small, going either way, you sort of see the accuracy drops quite significantly. So this is what I was saying at the very beginning about your training ChatGPT. We really care about getting good accuracy, but how you're tuning these parameters does make a big difference in how well your model is going to work.
This is for steps, like assuming you're taking n steps.
Yes, this was for maybe 1,000 iterations or something. But what you can sort of see with our fuse scheme is that because we have an automatic way of learning what the step size parameter should be, we don't have to deal with these step sizes, so we just have a fixed level of accuracy. And what you basically find from all the examples we've looked at is that because we have this logarithmic penalty we're paying, compared to knowing the actual true ideal step size parameter, we're a little bit worse when we don't know the truth, but we're much more robust. And on the right-hand side, what you can sort of see is that as we run this algorithm for a number of iterations, what you have is you have either slow convergence, which is what you sort of see at the bottom here. So this thing is converging slowly, and that's because this bit's always fun because I'm colorblind, so I find it hard to disentangle these. But for these ones, the step size is too big. Okay, so it's not converging. And for the other ones, it's too small, so it's converging, but it's just converging much more slowly. That's why you sort of see this one is sort of slowly going to where it wants to. And then for our method, it converges both quickly and robustly. Okay. This is the same but for SVGD. So I mentioned you've got these two different algorithms. You've got this launchman thing, and you've got this Stein scheme with the particles. It's the same story again. You have a grid of step sizes. And if you choose the step size for the Stein scheme in just the right way, then you get good accuracy. Alternatively, if you have our fuse method, then you don't have to choose any step sizes. And oops, okay, I'll just click that. Yep. And on the right-hand side, you have a number of iterations. And again, what you sort of see for our fuse scheme is that it converges to the sort of the best predictive accuracy quite quickly, and it tends to do so as well as what is the optimal. And the only way you know the optimal is if you just do lots of simulations with different with certain step sizes. Okay, so the last one I'll show you is this mean field neural network. So I was talking about this neural network, you got the number of neurons go to infinity. So this is the sort of posterior distribution you get for just two of the weights that you want to look at. And what you can sort of see is that for this mean field launching scheme, it sort of works okay, but it doesn't seem to sort of capture the distribution as well as the sort of fused scheme where you are adaptively setting the step size parameter. Something I didn't talk about is that the way to think about the step size is that it's not just a single scalar value, it's actually going to be a vector. And so if you have our adaptive sort of fuse scheme, what it's doing is it's able to account for the fact that you want to move maybe more in one direction than perhaps another direction. So for this one, for example, you have a step size parameter which is really good at exploring this axis, but not this axis. Okay. So I think that's the last slide I have. The sort of takeaways. So a lot of these sampling algorithms can actually just be viewed as optimization algorithms. I think that's probably the main message. And once you do that translation, so you see the connections between the two, it turns out there's a whole bunch of ideas from optimization which you can now put into the sampling context, basically. So something which we're working on still is looking at some of these cool new algorithms from the optimization literature to see what is the sort of sampling equivalent and can you sort of prove convergence rates for those algorithms. My last slide. Thank you. Any questions?
Yeah. How old is the that sampling and optimization analogy? Like how long have you been developing this?
Yeah, probably about 10 years at most. Probably 2016, 2018, people started to notice this sort of stuff.
And that Fokker type is that
The Fokker types we've known for a lot longer. That's a lot longer. So that's because that kind of comes from the sort of sampling literature, traditionally like the 80s or something, when people were looking at these launching schemes. But
as the gradient descent of the thing.
so that goes back to probably 2008-ish. There's the Ambrosio paper. There's also the Jordan Kinderleyer Otto scheme, the JKO scheme, which is 2008. So mid to late 2005, 2010, that kind of region. But only the machine learning community kind of caught on to it about 10 years ago. And there's been a lot of work in the machine learning conferences looking at how you apply these schemes to different sampling algorithms.
in a compared to traditional XMC, we have the optimal size, right? We can figure out like optimal step size. Can you relate that with that?
Yeah, that's a really good question. So, in the so one thing I didn't talk about, I sort of cheated slightly. So, when people do this sort of sampling stuff, what's hidden under the hood is that there's an acceptance probability. So, as I say, this algorithm, the launch algorithm, is making proposals, but it only accepts them with some probability. Okay? And there's theory to tell you that for this algorithm, you want to accept about 57% of the time. So you can choose your step size so that you accept 50% of the time. And if you look at the random walk, it's 23% acceptance. And so you choose to do that. The reason that this particular piece of work we're doing now with Fuse, the reason that we think it's interesting is because you don't have accept reject anymore. Okay, so for the SVGD or the unadjusted launchment algorithm, people use those because you can use stochastic gradients, which is what you care about when you have huge amounts of data. Okay, you can't use stochastic gradients here. You don't get samples from the true distribution, but you can for ULA and for SVGD. But the problem is you no longer have a step size, so you no longer have an acceptance probability. You just accept everything, essentially. So because there's no acceptance probability, you can't tune the step size based on an acceptance probability because you just don't have it.
Does that make this more efficient?
You mean the traditional NCMC or
Not traditional, but
our stuff?
you accept everything.
Yeah, so the problem is when you accept everything, you introduce bias, right? So that, with these types of schemes, when you're rejecting stuff which, if you have a point here, right, rejecting because it's not in the distribution. With the launchment stuff, you don't reject it. So that's still part of your sample. The hope is that your algorithm is efficient enough, but it's generally exploring in this space. But this is why you get this small amount of bias. So it's an asymptotic bias, which is why I was sort of saying you can only ever get one of a routine convergence rather than one of a T, even if it's a smooth function. It's because you've got this bias that comes in because you don't have the rejections anymore.
Any more questions? If not, I think, yeah, let's thank Chris again. See you at the next Mars seminar. So the usual host, Maciek, will arrange that for then it will be next week or the other after. But yeah, you will get an invitation. Thank you.